Hello all, my name is Pratyusha Kalali. Welcome to the presentation, Introduction to Systems Engineering. Topic is Satellite Communications. This is the final presentation of my project. Moving on, these are the contents of the presentation. I'm going to discuss Systems Engineering, Satellite Communications, Starlink, SpaceX, and what they have accomplished in this domain. I'll be relating each concept in systems engineering development to what SpaceX has done at each phase, giving more insight into how each phase is crucial. First, we'll dig into systems engineering phases, which are concept development, engineering development, and the post development stage, which is nothing but production. We have a further breakdown of each phase, which includes needs analysis, concept exploration, and concept definition. And engineering development stage is further divided into advanced development engineering, design, integration, and evaluation. Post development stage we have operation and support, which helps with maintaining the system and helps with the success of the system. Later we will discuss challenges and references. With that, moving on. Introduction. In systems engineering, we have a broad perspective focusing on how a system functions as a whole and its interaction with everything around it. It's about understanding the big picture and ensuring all the parts work well together with the outside world. This approach helps in building complex systems, guiding us to blend all the pieces effectively to meet the overall goals and requirements. It's not just about the individual parts, but how they come together to form a cohesive functioning whole. And here we have satellite communication. So, what are satellites? Satellites are man made tools orbiting the Earth, crucial for our global communication. They make things like daily weather updates possible. System engineering is about creatively solving complex problems by considering every part of a system and how they work together. It's about looking at the big picture, all to make sure these vital satellites do their job right, from sending signals up to the satellites, which we call uplink, and to getting data back down to us through downlink. Each step is vital for keeping us connected and informed. Now, types of satellite communication. Communication signals travel in different modes, like ground waves close to the Earth's surface, sky waves that bounce off the ionosphere, and space waves that move directly through space. Satellites are set up high above Earth to allow these signals to travel over long distances. Even when the starting point and destination can't see each other, this satellite communication has transformed how we stay in touch across the globe, making it a cornerstone of how we share information today. Starlink, engineered by SpaceX. Starlink is set to deliver fast, affordable internet to areas where connectivity is low. The focus is on the system's total efficiency and performance. Starting from the announcement in 2015, it took 4 years to launch the first batch of satellites. Now there are approximately 3,580 satellites orbiting at a relatively low altitude, which allows for quick and reliable internet service. SpaceX innovation with the reusable Falcon 9 rockets has cut down costs and lessened environmental impact. Starlink's mission is to provide fast broadband to areas where reliable internet aiming for global reach. It's a game changer for the 3 billion offline people worldwide. With low latency, its network of small satellites in low Earth orbit outperforms traditional ground networks. After a significant launch in 2023, Starlink plans an extensive constellation of satellites to revolutionize internet access globally. Here, the life cycle of systems engineering. This image illustrates the life cycle of systems engineering broken down into three main stages: concept development, engineering development, and post development. Each stage has inputs and outputs. Concept development starts with operational deficiencies and technological opportunities. leading to a defined system concept. Engineering development takes these concepts, adds system functional specification, and results in a production system. Post development involves system production specifications and culminates with an installed operational system, complemented by operations and maintenance documentation. Concept development. In the concept development stage of systems engineering, we have start by evaluating the current system and exploring alternatives. We prioritize needs and challenges to select the optimal solution. This involves a thorough analysis of systems plans and interactions, ensuring new concepts are viable. The process includes three key steps: need analysis, where we identify and prioritize requirements; concept exploration, where we brainstorm potential solutions; and concept definition, where we develop a detailed design to guide further development. Need analysis in systems engineering is about ensuring there's a real need for a new system that provides more benefits than the current one within known constraints. It involves evaluating if the new system should leverage advanced technology for better performance or address specific deficiencies of the current system. This analysis is critical in justifying the development of a new system and setting the stage for its design and implementation. Coming to Starlink need analysis. Starlink aims to provide high speed internet to remote areas lacking connectivity. It's part of an ambitious plan to redefine internet from space and make it widely accessible. Starlink's development was driven by both technological advancements and market needs, resulting in a network that offers speed and efficiency at lower costs compared to competitors like VSAT and HughesNet. With a focus on under-reserved areas, Starlink is tapping into a significant market of disconnected regions. In the concept exploration phase for Starlink, we shift from just thinking about systems operations to the engineering aspects that make it all work. We have assessed operational needs globally and tested prototypes like Tintin A and B satellites to refine Starlink designs and understand satellite interactions better. This crucial phase keeps stakeholders in the loop, with developments ensuring the project aligns with Starlink goals to connect the world. And the image depicts a flowchart for the concept exploration phase in systems engineering. It starts with the needs analysis phase, assessing operational requirements and analyzing predecessor systems. This leads to an operational requirements analysis where requirements are refined. From their performance requirements formulation involves deriving subsystem functions and formulating performance parameters. Then the implementation concept exploration considers different implementation concepts. This process ensures all system components are aligned, meet performance standards, and are feasible. The final phase integrates and validates these performance characteristics to solidify the concept definition. In the concept definition phase of systems engineering, we select the most promising system concepts after evaluating various alternatives. This selection is based on the detailed trade studies that consider several crucial factors. 1. Operational performance and capability. How well the system can perform its intended functions. 2. Program cost. The budget required to develop and implement the system. Program schedule is the third. The timeline for the system's development and deployment. And the fourth is risk. Potential talent challenges or issues that could arise and their impact on the project. These criteria ensure that the chosen concept is not only technically viable but also cost effective, timely, and risk managed. Coming to Starlink concept definition. Starlink concept definition phase for Starlink, the focus is on the satellite's technical capabilities. Starlink satellites utilize laser links that mimic terrestrial fiber connections, enabling the transmission and relying of signals across space. This design aims for dependable long-range communication, unhindered by its curvature. The satellite orbits are precisely calculated to avoid space debris, minimizing collision risk. This strategic design is crucial for maintaining the integrity and safety of the constellation. Coming to engineering development stage. So during the engineering development phase in systems engineering, the focus is on taking the conceptualized design and rigorously testing its prototype. This phase is about ensuring the system functions as intended and meets all predefined requirements. It's a meticulous process that includes fine tuning the design and integrating various components and also conducting thorough assessments to address any potential risks or challenges. The ultimate goal is to validate the system's readiness for production while adhering to cost considerations and ensuring compliance with safety and regulatory standards. Now we have the advanced development stage. We are here. So let's dive into it. The advanced development phase in systems engineering bridges the conceptual groundwork laid previously with practical application. It's about refining the prototype based on rigorous testing, ensuring it meets the real world demands it was designed for. This stage is critical for identifying and mitigating potential risks, optimizing the cost effectiveness of production, and confirming adherence to safety and regulatory standards. The process follows a structured path from advanced development to detailed engineering design, leading to integration and comprehensive assessment, setting the stage for a system that's ready for deployment. Starlink is working hard to make sure that internet satellites are safe and affordable. They do lots of tests to find and fix problems, which helps them save money and get better at making satellites quickly. They also use special tech to test flying rockets safely back to Earth. This shows how seriously they take the safety and cost of their space missions. Safety testing of prototypes, cost saving measures, rapid prototyping for innovation, and risk management strategies, especially with rocket re entry, are further phases. So, coming to if we discuss further into advanced satellite technology, like for satellite design, Starlink satellites are designed to be compact and lightweight, optimized for mass production and deployment. They come equipped with multiple high throughput antennas and solar rays. Onboard propulsion. Each satellite has a krypton powered ion thruster for orbital adjustment and deorbiting. Inter-satellite links. Satellite is implementing laser-based links for direct satellite to satellite communication, reducing reliance on ground stations and improving latency on coverage. Expanded network architecture, and then we have low orbit or low Earth orbit constellation. The satellites are placed in low Earth orbit for lower latency and higher bandwidth scalability. The constellation is scalable with plans for thousands of satellites to improve global coverage and capacity. User experience improvements like phased array antennas. The user antennas can dynamically steer beams for a reliable connection, easy setup. The dishes are designed for simple plug and play setup. Sustainability and safety measures are for the debris mitigation. The satellites are designed to burn up in the atmosphere at the end of their life cycle. Regulatory compliance. Starlink ensures compliance with space safety and debris mitigation. Future goals and innovations also include Global connectivity, aiming for providing high speed internet globally, especially in under-reserved areas. Integration with cellular networks, potential for expansion. Moving on, we have engineering design. In the engineering design phase, Starlink enhances the initial prototype to meet specific testing standards, ensuring that it can withstand the practical demands of space. This phase results in a more defined prototype ready for deployment. The installation of Hall thrusters on Starlink satellites is crucial, contributing to the project's success factors like efficiency, quality control, cost effectiveness, mass production, management of space debris, air traffic navigation, which is like all of these are very important. So, especially when it comes to like management of space debris, later in the challenges we are gonna dig more into this because it will be a big problem. So imagine like a huge chunk of debris, like let's assume like we have so much debris in the space and they form into a chunk because we are now launching so much satellites and so much of our waste we are taking them into the space and everything is inflammable in the outside world, right? When it comes at a certain speed towards the earth, it can form into a comet. That's how comets hit our earth, as we all know. So management of space debris is like very much important in this systems engineering. I mean like maintaining the any system. So Starlink has done some good work for it, and also it is doing even more work uh, to make sure that they manage the space debris well. So systems engineering, this phase, engineering phase takes care of it. But even though it remains as like a major challenge, but still there is some improvement with this management. And also air traffic navigation. Oh my god, this is also like a big thing. So Starlink actually had some really good success with traffic management and also minimizing environmental impacts. What uh, in the manufacturing of the satellites or even in the maintenance, even when it goes up, the fuel that is used, it is like so many tons and it produces so much pollution. So that environmental impact also need to be managed. Otherwise, or offsetted at least, even though it was not. I mean, there are some unavoidable emissions during the process. So, what Starlink or any company does or have to do is managing the emissions by letting in only some emissions and by controlling whatever uh, can be possible by offsetting and by reforestation, whatever. So, ultimate goal is to reduce the environmental impact, and that can be done in this engineering phase. So this advanced engineering stage is prototype model. This stage strives to provide a better engineered prototype with clear test requirements. So yeah, these elements combined ensure the satellite's operational success and sustainability. And also I forgot to mention about the Hall thrusters are installed in Starlink satellites during the engineering design phase. Moving on, integration and evaluation. In the integration and evaluation phase, which is the final subphase of the engineering development stage, the primary objective is to ensure that the intended design aligns perfectly with the actual design and is well suited for its intended use. While in an ideal scenario, all engineering phases would be flawlessly executed, in practice, this rarely happens, especially in large projects. During this phase, the outcomes and the performance of the system are thoroughly evaluated and compared to the operational requirements that were initially defined. during the need analysis stage. Like we have just gone through the need analysis phase and what Starlink has done, right? So this step is crucial to verify that the system meets its intended goals and functions effectively. Key activities in this phase include system integration, where all components are assembled and tested together to ensure they work seamlessly, and user testing as well. Exactly. So during the integration and evaluation phase, the system goes through the multiple layers of testing. It can be user testing, manual testing, which includes manual testing and the simulations and whatnot. So everything is has to be done during the integration and evaluation phase. If all the engineering phases are flawlessly developed, this stage can be omitted actually, but nevertheless there might be some human errors that might have been got involved during the phases, no matter how perfectly it is done. We all know like no human is perfect accurately 100%. Even AI as well, we cannot trust 100%. So testing phase is like the most crucial phase. um, if if we are not 100% or even 101% sure during this phase, um, we shouldn't launch the product or the system as well. So we all know like how critical this phase is. Like now, no matter what phases the system has gone through, integration and evaluation is the very much critical phase in our system engineering development. So uh, the outcomes of this stage are compared to the operational requirements. The operational requirements which were brought in the beginning of the development phase, or the requirements analysis and gathering phase, uh, so that were initially established during the need analysis stage as well. Yes. Okay, where the system is evaluated by end users to identify any issues or areas for improvement. This phase plays a critical role in ensuring the success and functionality of the system before it is deployed for its intended purpose. Yeah, that's it about the integration and evaluation. Moving on, in the post development stage, the goal is to transform the design and engineering concepts from the previous engineering development stage into actual components. Yes, exactly. So, whatever each phase, in a system that has to be developed, it's not like we build everything together, gather every requirements for everything together. No, right? So, for satellite, fuel related structure is developed separately, and the thruster related is developed separately, and it goes through the entire phases that we have just discussed. So during the post development stage, we bring it all together, and we make sure that all the components are working together as well, where they might be working individually in a perfect way, but once we integrate, like in the previous stage, while we integrate and evaluate, we should make sure that it works exactly as it is intended. Okay, this phase ensures that price, dependability, and safety standards are simultaneously addressed. It involves the implementation of hardware, software, and assembly process to bring the system to life. Efficiency is a key focus during this stage, aiming to optimize the manufacturing process for efficient and scalable production. Some instances of production include providing internet access to Ukraine and enhancing the capabilities of the armed forces. Yes, these are some of them further. Yeah. Yes, the operation and support phase. This is like the ultimate component of a system engineering project's whole life cycle and marks the conclusion of a system. So without this phase, right, there is nothing after that. So this phase is like a continuous phase, even though the initial or the phases until now that we are discussed are ended at some certain point in time, but the operations and support phase is like the life of the system. They take care of the system, I mean it take care of the system, and it makes sure the system is working as intended. Yeah, so I have mentioned it marks the conclusion of a system engineer's role and duties. The primary goal is to provide post-production support and maintenance for the system to extend its life cycle. Customer satisfaction is a key focus during this phase, as efficient support, operation, and support are crucial for ensuring customer satisfaction with the system. By prioritizing customer satisfaction, Starlink can build a loyal user base and increase the likelihood of repeat business. Well, now we're here at the challenges. Challenges of a Starlink project include Kessler syndrome challenges, like mitigating collision risk from self-perpetuating space debris, growth due to collisions on Earth's orbit, known as the Kessler syndrome, is a complex engineering and operational challenge. It requires accurate debris tracking, characterization, and updated collision prediction systems for collision avoidance. That's what we discussed during integration and evaluation phase also, right? What Starlink is doing, Starlink has made some tremendous success in that phase. Cost challenges. Addressing the Kessler syndrome through space debris removal and mitigation programs comes with substantial expenses. This includes the costs associated with launching missions to remove or redirect space debris, designing satellites with shielding for collision protection, and the significant financial burden of launching satellites as exemplified by the Starlink program. Moving on, yes, here we have the more challenges like Starlink faces regulatory challenges that includes regulatory cooperation. Ensuring international cooperation is crucial for addressing regulatory challenges related to space debris mitigation. This involves standardizing approaches to tackle the Kessler syndrome and enforcing regulations that mandate spacecraft to adjust their orbits or transfer to high altitudes at the end of their operational life. Impact on astronomy. The presence of space debris can have adverse effects on astronomy. It can lead to light pollution, creating satellite trails that obstruct astronomical observations, right? So, astronomical observations are very crucial. That's how we know what kind of challenges or what kind of threats that we pose. So, yeah, the impact on astronomy is like a major challenge in terms of satellite communications. Additionally, large satellite constellations, particularly those for global internet coverage, can generate optical interference and disrupt optical and infrared observations, posing challenges for ground based astronomy. Yes, exactly. Yes, references. I'm very thankful for all the content that we have online, especially from Starlink Wikipedia. They have like really good uh, details about it. So without that, I wouldn't have been able to refer to each stage and the accomplishments that they have made, and that actually gave more depth into the systems engineering phases that we have just discussed with like clear examples. And also please note that the class lectures, PowerPoint slides from Brightspace, and the systems engineering RTV Silicon Silent Application System article. So yeah, these are not publicly accessible URLs, so they are not included in the list of references. So here are more links for the references that I have used. That includes like who is Starlink really for, and Starlink satellites, facts, tracking and impact on astronomy, and the space review, the promise and challenges of Starlink. Thank you so much for all the information that is available and I'm able to use, and thank you for coming with me through this entire presentation. Uh, as we have explored Starlink and systems engineering in satellite communication, let's keep reaching for the stars and connecting the world. If you have any questions, feel free to ask. Together we can make amazing things happen. And I'll attach these references to the link in the comment section as well, and also in the description of the video. Feel free to reach out to me if you have any questions. Would be happy to help. Thank you.